Alrighty. Hi, everybody. How are you? It's great to see you. Welcome for Global Hack Week. And if this is your first time with us, welcome to the program. If you have been hacking with us all week long and you're a veteran now, it's great to be at the final stretch, isn't it? I think this is one of the last streams for the week. So then you'll get a nice rest. But yeah, actually, I think we have a few more even past this one. There's one on Matplotlib, a Chrome Dino event, and then another technical stream, and then closing ceremony. So it's gonna be great. But before we get started today, I want to have you all check in for the event. This is super important. It lets us know what you're interested in. We can get a sense of the sorts of content that you like to see, and it also helps us just show folks that that our community is enjoying Global Hack Week. So give it a shot at registering. It's super helpful to us. All right. So today what we have planned is vision transformers. And I have multiple things to show you regarding that. And we're going to start with a slideshow here. All right. So, vision transformers. What are they? We're going to put those in there. Sorry about that. I have a little bit of an error there, but I didn't actually mean to put anything here. That's just my own issue. But what are vision transformers? The importance of image classification, and what will you learn? Those are the main things. So vision transformers are essentially a way of using image data to gain insights. And it's very important in AI. You might need to do object detection or image classification, as we did in our last workshop with Are Bananas Ripe and things like that. And then what will you learn in this tutorial? There's a lot that we will learn. We're going to learn how to train these models, and we're going to learn how to get them to do what we want to do. So yeah, I'm excited to get started with you. You'll need a few tools and libraries. We're going to use Python. That's the most common ML language. And the reason is because there's so many algorithms that are implemented in Python, or packages that you can download to quickly deploy your machine learning models. So it's really helpful to have a knowledge of Python if you're a machine learning engineer. And we're going to use TensorFlow. Now, TensorFlow is a machine learning framework for training, evaluation, and algorithms. You can use TensorFlow. You can also use other alternatives. There's PyTorch, and there's several other machine learning packages, frameworks. But we're going to use TensorFlow for today. And the TensorFlow datasets module is a bunch of cloud-hosted datasets. And today we're going to be using the Flower dataset. And the reason we use those is they're publicly available, and they can be compared with one another pretty easily. TensorFlow Hub is a module that hosts pre-trained machine learning models. So that's a really great place to go for those. And Matplotlib is a data visualization package. So it's a really good way to see if our results are working. So let's talk about the data set first. Well, actually, before we get to that, I want to show you a link to this this Python notebook that I have set up for us. And I'll send it in the chat. I want anybody to be able to view it. So it's in Google Colab. So you'll need to get a Colab account to access it. But we're going to walk through the first part of this because we've already talked about a lot of this. The first part here is we're going to do some image classification with transformers. And we're going to use the publicly available Oxford 102 flowers dataset, which contains 102 types of flowers commonly found in the United Kingdom. Okay. So first we will do setup and installation. We're going to list all of these important libraries. And once we connect, we're going to connect to you can actually just connect to a CPU. You don't need to connect to a GPU for this one. Actually, I think it's better if you connect to a GPU. So why don't you go ahead and try and connect to a GPU? It's totally free, which is so cool that in Colab you can actually get a free GPU instance. Pretty high traffic today, it seems, on the GPUs, unfortunately. We might have to go for a slower CPU. Let's try and run this. It can take quite a bit of time. While we're connecting, I'll go back to our slides. So we're going to import the necessary libraries that we talked about. So TensorFlow datasets, some of these modules that we don't already have. All right. And we're going to load in the Oxford Flowers 102 dataset in this next cell. So you're going to use the TFDS or TensorFlow datasets library to .load Oxford Flowers 102 is the ID of the database with info and as supervised. So what that means is that with info, we're going to load all of the associated data with it, not just the images, and the data itself. But we're also going to check off as supervised, meaning that we're going to load the dataset as if you were going to train as a supervised model, because this Vision Transformers classifier is a supervised model. Okay, so when we do eventually connect to our runtime, we'll get all of that sorted out. All right. So the Oxford 102 flowers dataset contains some key characteristics. There's characteristics like the number of classes. We already know this number of classes and types of flowers is 102. Okay, so there's 102 classes. And then the image itself has many features. So we talked about features in our previous one. Oh, how do I register for 23AI free VirtualBox? Could you tell me, Yuvraj Gupta, what is that? Because I did not see that when I was running this code. Just let me know about that. Okay, and why use public data? Well, it's great. It's able to compare across the model development community. It's freely accessible and can actually be very high quality when you need it. So we're gonna have that public data set in our workshop today. And once you type out this cell, it should run. You can see that there is it did completed 100%, 3 out of 3. DI size 100%, extraction completed 100%, and there are a lot of files here. In fact, there are 600 megabytes worth of flowers, which is a lot. Okay. And when we do have these flowers, they have the following numbers attached to them. So let's say 72 could be one number, 84 could be another one, 70 is another one. And so the reason we store numbers instead of letters is because, or instead of words, is because the numbers are more condensed information, more standardized. And so it's a lot easier to have those attached to the flowers. Okay. Then the next step is going to be data pre-processing. So we're going to do some pre-processing of these images in deep learning. And does anybody know why you need to pre-process an image here in this case. Actually, we ran into this in our last workshop when we were looking at transfer learning. So nobody really knows about that. That's okay. The pre-processing is going to basically happen because we need to match up our image to the input size for the model. Okay, so we are going to load in a specific model or a specific vision transformer model that is going to accept images of 224 by 224 in the XY direction. So if we look at the image with the 3 channels, those 3 channels will have specific dimensions. So we'll use X and Y for that. All right. So let's go back into our notebook. It seems like we're still having some issues getting connected, but I just wanted to show you a little bit of how this would look like. So when you run this file, it will store the pre-processed data into train data and test data variables. Okay, and I want to highlight a few things about this cell. So first, as we said, we have these 224 by 224. That's going to be very X and Y related. And then this dividing by 255, well, that's because you have channels, color channels, which are hexadecimal, RGB, whatever you want to write. But I think actually here we're writing RGB, and they'll have a value out of 255 being the most full on any color channel. So if you divide by 255, you will normalize to the 0 to 1 range. Okay. And so you'll return these two things, image and label. The label is not really changed in this function, but the label is just those numbers. That's just a string of those. Vita says, does the input need to be in square size for this model? That's a great question. The answer is no. It doesn't need to be a square. It could be a rectangle also. But the way the transformer works is it splits into patches. And I'll actually describe that in a little bit, so it'll be really neat to see that. But we will check that out really soon, and we'll see that those patches are not, they don't need to be square. Okay, so now the next one would be to actually visualize these, and that's why we need that matplotlib library. And it's because we're going to basically plot each of these images on an array of 3 by 3. So we have 72, 84, 70, these different images. And we're just going to plot them because we want to see what is this looking like. And this is the raw data we're looking for. This is a great question, though, Dino Vita. And because we are having squares, you can see they're all squares. So it's a good observation. But yeah. All right. So back to our slides here. I want to emphasize something else. So the map that we do, .map function, that is going to apply this function, this preprocess function, to all of the members of the test and train data sets. And then .batch32, what that does is it actually splits these flowers into sets of 32. And what that means is that the model will be able to adjust itself to run off of 32 instances each time and retrain. All right, now we're going to look at vision transformers a little bit. And I want to really dive into this idea because it's a little bit complicated. So I don't know if you all have heard of NLP and ChatGPT, but the idea with those is actually transformer. They take a long sentence and they split it up into tokens. which each have some meaning to them. So, for example, transformer could be 3 tokens, transformer, or it could be split into just 1 token, transformer. But typically, they will split them into really small pieces of meaning and try to predict what is the next token. Okay. In this case, we have a image, and we use what's called a patch to split the image into equal patches. And on this left side, at the beginning of this animation, they split an image of a tree into 9 patches. So the image could be also rectangular. It doesn't have to be square like this, as long as each patch is exactly the same size. Okay. And then they flatten the patches. So they flatten the patches out into a line. And that line is similar to a sentence, how a sentence might be composed of many different words. So they not only have meaning within each other, within each patch, but they have some meaning in relation to each other, just like a sentence would. So we can then encode them into the transformer and a transformer encoder, and use the MLP head as a final layer to get the class that we want. So that class, as a reminder, could really be anything, anything that you want to predict. All right, and so that brings us to our model setup stage, where we're going to be doing this model setup. Oh, yes, I have this on Google Colab here. So we're going to load the pre-trained model from TensorFlow Hub. So let me show you this model on TensorFlow Hub, which is now Kaggle. And you see, this is a collection of new vision transformer models fine-tuned on ImageNet 1K. What is ImageNet 1K, you might ask? Let's check it out, actually. Should be cited down here. I'll look at a lot of this stuff to really understand what is vision transformer. But I want to bring your attention to ImageNet. So a lot of people don't pay too much attention to these data sets that are being used, but there's a huge amount of data that we get. So look, a tiger cat is one image here, Yorkshire Terrier, an airship, a balloon, a space shuttle. Just so many different pictures of different things, a gown and a standard poodle, and yeah, all kinds of things. And so I suppose that the vision transformer is being trained based on this. Let me show you the original paper for this idea. It's Transformers for Image Recognition. So just to really hammer home this idea, they have the flattened patches, which are here, these embedded patches. They normalize those. So we already did the normalizing. I think you might remember in that function that we wrote, we had some normalizing where we divided by 255. The reason we do normalizing for transformer is because we want to make sure that the algorithm is able to actually operate efficiently and find a solution. If we have them not on a 0 to 1 scale, then the algorithm can sometimes fail to do that effectively. So it's just much better to have your data normalized. The multi-head attention. Could anybody explain that? Does anybody know what is multi-head attention in this green box here? Oh, thank you, BlavKZ1. That is super helpful because I was not sure about that person's question. So thank you for answering that. Yuvraj Gupta, if you have that question still, you can check what Blav KZ said. And Dinovita said, may I have the link to the paper? Absolutely. I just sent it in the chat. It is an archive chat. So you can just check that, archive PDF, excuse me. And yeah, so nobody really said what is multi-head attention, so I'm just going to explain that. That is telling us which of these patches to pay attention to. So if we're looking, for example, at this this steeple patch, right? Maybe we should also pay attention to this other steeple patch, and that might tell us what what this object is. If we're looking at the ground, maybe more relevant to look at is the sky, because it will give us a more diverse piece of information. So it's actually kind of hard to tell which of these patches will be related to which ones, but the multi-head attention will update over time the importance of these patches relative to each other. It's kind of like in a sentence where an adjective would be really relevant to a noun that is right after it, or in English at least. And so you can use that multi-head attention scheme to design that. So anyway, then after multi-head attention, there's another normalizing step here. And then it goes to the MLP head, which is a very final layer, and it will condense this into a classification, which happens at the very last bit. So yeah, that is how the model works. I don't know if there's anything else in this paper I wanted to show. I just kind of wanted to show you that that idea there, but maybe this is something else to look at, because look, they actually showed that Vision Transformer can do our data set quite well, our Oxford Flowers data set. So we're going to be looking for a similarly good performance, 90+%. See what we can get. All right. You might notice that they have these VITB, VITL, VITH. Let's see if we can figure out what those mean. So VITB is base, VITH is a really large model, VITL is also. So I guess B and L, L and H are a little bit bigger. And then when we have this divide by 16, it's my understanding that that is the patch size. So yes, check that out. VITL means the large variant with a 16 by 16 input patch size. And you can see that the models with a smaller patch size are generally more expensive, but they're also going to be more accurate. So the smaller your patches are, the more accurate your model will be, but also the longer time it will take to train. All right. So let's go back to our data here, our Kaggle, and you can see that they have several of these models, S, B, and L. I've been using the S one because it's a little bit small, I think a little bit smaller of a model. But you're welcome to use any of these in yours. You just have to replace the model name in the URL. But check it out. They've got some model results on what these different models can do with these various data sets. Looks like the S16 is usually better than the R26 S32. That makes sense because the patch size here is bigger, right? And so here's another example. You can see that the larger patches, B32, even though it's a very big model, still worse than the 16. So a lot of these vision transformers, and look at this one, 8 patch size. That's super small. You can see how great that is. I think that's the best one of them all in terms of accuracy on this. Yeah. So you can replace it with whichever one you want, but I have in my code cell, I have it as this URL here, tfhub.dev/sayekpaul/VITS16 classification/1. Okay. And then to build the model, I actually have two steps here. So there's first this this vision transformer model that we put in as the first argument to a sequential Keras object. So that's going to connect all the layers together. And of course, we want it to be trainable, this model, meaning we can adjust the values of things like the multi-head attention and the patch encoder. And then we also have the dense layer, which connects these to the numbers of classes. So we're going to have one for each of these classes and have an activation function that will essentially try to map whatever output comes from the vision transformer into a discrete class. Okay, one of 102 different kinds. And then in the end of this cell here, we have model.compile, and we input optimizer equals atom, loss equals sparse categorical cross entropy. I want to talk a little bit about those before we move on. So let's share this tab, this file. The atom optimizer. Now that is an adaptive optimizer. It will tell the computer how it should go about adapting the parameters of the model in order to fit better to the data. So you can choose a different optimizer, but atom is by far the most common one. And then sparse categorical cross entropy, that is a loss function. And so the way that works is it's going to tell the computer how to score how it's doing so far. So if that loss function is high, it means that the model's not really doing very well. But as it gets lower and lower, hopefully the optimizer can help it get lower and lower by tweaking. It will become more accurate. And so that is sort of what those bullet points are referring to there in the compile. So yeah, that would be the next step in the thing. And then we'll do model training. So model training is just about fitting the model. Does anybody know what fitting the model means? Even in the abstract, what does it mean to fit the model? We really do see this all the time. Model.fit. Does anybody know what's going on there? And what does the fit depend on? What does that process depend on? There's several things that we've already mentioned that it will depend on. Yeah, so I'll actually show you about that. Basically, it's going to depend on all of these, right? The model itself, the architecture of the model, how it's compiled. So what is the associated optimizer, loss function, and metric by which we're going to evaluate. But the fit is really taking all of this together and operating on this model with a specific training data, validation data, and epochs. Now, we're going to talk about the epochs next. Epochs plus batch size are really important for training. So batch size, we already talked about that. It's 32 each. So each of these training data instances will have 32 different flowers in it. Okay. Now we could break that down into even smaller batches, and then the model gets even more opportunities to recalibrate, right? But we also don't want to make the model go on forever and ever and ever. So for that reason, we're not going to just let it, go on like that. The other thing is epochs. So epochs is saying how many times do we want to run through the data? Okay, And so running through the data is another huge question because every time you run through the data, you have another chance to adapt the model, get a little bit closer to that convergence. But you also don't want to run it too many epochs because you might not get any benefit and it would take a really long time. So epochs will linearly increase, as well as batch size. They will both linearly increase the time to train the model. Okay, so you want to be very mindful of those. But Vida says it has something to do with learning rate. It does. I mean, in the sense, we're talking about giving the model enough time to learn the solution. Although we don't assign a specific learning rate like we do in some other models. All right. So I also want to talk about what is the concept of convergence, okay? Because I just mentioned that we're talking about learning rate, we're talking about all this kind of stuff. Well, concept of convergence means that I can get the model as close as I want to zero loss, but you need to tell me how many epochs I can train for. So, and I'll tell you how many epochs you can train for. So let's say I want to get below 0.5 loss, right? Well, if you want to get below 0.5 loss, you only need to train for 3 epochs. And then you say, and I get down to 0.1, let's say. And then you say, well, now, Stephen, I want to get down to 0.05. I can say, well, that's fine, but you need to then train for 4, 5, 6, 7, 8, 9, 10 epochs, right? And you'll be down to 0.05. And then you say, I want to be down to 0.01. So maybe that's like 1,000 epochs or 10,000 epochs or something. And you can get down to 0.01. And it'll just keep going like that. But eventually, it will never go below some certain value, okay? So in this case, maybe the model has already converged because, to be honest, we're not really getting increasing, we're not getting improvements with each epoch. So maybe it converged around 6 or something, maybe even around 5 epochs. But convergence is how you know that your model is done training. And you can see it in the training accuracy too. So this is the accuracy, 30, 0.3, 0.7, 9, and eventually we get up to almost 100% accurate. Actually, I think we do get up to 100% accurate on this data set because we've got it in these big batches. We can actually get 100% accuracy. But yes, it does actually then converge. Okay. So let's look at this in a more material way. I have it from a previous run. You can see in the first epoch, we do 32 sub batches here, and we get a loss of 4 and accuracy of 0.27. All right. And then you say, hey, I want higher accuracy, right? I'm going to do another epoch. So you get to epoch 2. And we find out that the loss is 0.54. The accuracy has jumped almost to 0.9, right? We're almost to 0.9. That's pretty cool. And then I say, all right, I want even more. So let's go to epoch 3 here. All right, now we're up to 0.99 accuracy. We're getting really, really low in our loss. 0.1. So we went from 4 to 0.5, which is a drop of like almost an order of magnitude. And then in the third epoch, we only moved down by an order of 5. Okay, so we went from 0.5 to 0.1. But we still are moving hugely. And our accuracy's gone up by about 10%, which is great. And this is our this last one here is our validation loss. Okay, so our validation loss is what we really care about in the end. Right? Does anybody know the difference between loss and validation loss? Hi there, Wind Slash. How are you? It's awesome to have you here and welcome for the stream. I was just asking about the difference between loss and validation loss. Anybody who is familiar in the chat. And I'm going to give away the answer. Loss is the loss function as applied to the training data set. Okay. So if you have the training data set, what is going to be the difference between what is predicted from the training data set and what is the actual value? That typically, that number can get really low, even along successive trainings. And in fact, it will almost always get much lower than the validation loss. If you have a really big discrepancy and the validation loss is not going down, it means you could have an overfit of your data. All right, I'm going to put that up on the screen. Overfit. It implies that your model has learned the training data set so well that it no longer is representing a meaningful prediction. Because when you apply it to something new that the model's never seen before, it doesn't know what to do. It's learned the training data sets so well, it's not sure what to do. It's almost like if you were to tell a kid to memorize the times tables of 5, 4, 3, 2, and 1, and they know every single one, but you didn't ever teach them how to multiply. And if you didn't teach them how to multiply, when they saw the 7 times tables, the 8 or the 9 or the 12, they'd have no clue how to solve it. And so that's kind of what you can have happen with overfitting. All right. So that's kind of an interesting thing. You can see each step is taking about a second, and the total for each one is about 30 seconds each. So yeah, in total, this whole training took, about 5 minutes to complete on the GPU. We're probably gonna have to use the CPU to actually get ours running today. Let's check it out. We're having a really hard time getting a runtime. I think a lot of people are using Colab right now. All right. So that's it. That's a little bit about fit. And we talked about convergence as well. Yeah, I mean, we have it here too. Training loss is this marker, and validation loss is this line. So you see, you can drop really low in the training loss and training accuracy gets really high, but the validation accuracy will never really converge to that same value. There's always going to be a little mismatch, and we can think of that mismatch as kind of a lack of understanding on part of the model, because it's just really fundamentally misunderstanding some fraction of the test cases that it sees. Luckily, in this case, it's not too bad. But yeah, let's look at some results. So here are some correct predictions on the top, and some incorrect predictions on the bottom. You can see if we have some pictures that are, it seems like the model does really well on these pictures where the flower is like basically head on. I mean, you see this first one is totally head on. The third one is head on, fourth one. And also if the color is a really big contrast to the background, it seems like, for example, this red one, the white one, the pink one. Now, in incorrect cases, there's a few that are, so if it's really on an angle, it seems like that can be really difficult for the model. If there's a lot of shadows, for example, there's a lot of shadows on this and this hydrangea. And I think also the fact that the picture is kind of darker, there's not as much contrast in some cases. I mean, look at this one here. This one doesn't have much contrast at all, really. And this one on the right, it seems like those are cases where the model really is not sure what to do. And you kind of need to think of another solution for those. But anyway, we can program this ourselves. I added a little, I'm going to actually share these code cells so you can know how to do them yourself. It's this in number 9, I have some of these. So here is your training and validation loss plots, and here is your predicted classes. So we need to take the argmax of predictions. Does anybody know why we take the argmax here? Why that's important? It's related to our previous stream yesterday. Does anybody know? No? All right. Well, the reason we need to do that is because the model is going to work, the classification model is going to work by assigning a probability to each class. So it says, well, I think maybe there's a 50% chance that it is a 99 type and a 10% chance that it is a 72 flower and another 10% that it's a 20, a label 20. And they'll just give those assignments, but we want to know which of these is actually going to be the most likely, because we have to make a prediction in the end. You might remember in yesterday's we did confusion matrix. Okay, so we could make a confusion matrix with the false positives, true positives, false negatives, true negatives, and we need to have a concrete, discrete prediction for each test case in order to construct that confusion matrix. That's why we do argmax. And then we also will have these correct indices where we have np.where. There's a bunch of these predicted classes and test labels, and we'll get correcting and incorrect predictions out of those, and it'll tell us what those are. And then it plots the images according to some we'll get a few predicted ones that are correct and a few predicted ones that are incorrect, and plot them. So that's how we do that that image. Right. And next we'll look at evaluation and prediction. So evaluation and prediction is the final step. Okay, this is really what our meat and potatoes. We've done some validation to test to make sure it's not overfitting too much our model. We've done some training to calibrate the model over many epochs, many batch sizes. And when we do the evaluation and prediction, we should get a pretty accurate model. It looks like the accuracy here for our model is about 96.7 on the test data that we have. That's pretty high. It's not as high as some of the literature values, though. If we look at the literature values on Oxford flowers, some of these models are hitting well over 99%. Okay, that's pretty good. And we didn't quite get there. I think what we would need to do is use a little bit more computing power here. We would need to really go for a lot of epochs, maybe have it see it a lot more. Because look at this, a 2.5 thousand TPU v3 core days. So that's a lot. And you can see how it compares to a CNN architecture. So here's the ResNet architecture, which is not a vision transformer, but it is another state-of-the-art vision classification algorithm. And in almost all of the cases, a 14 patch beat the. It's also a high resolution, and those are the large models, L and H. So we're using S, which is the small model, so it could also be Y, but it's always beating the ResNet architecture in every single scenario. Super, super cool to see. I highly recommend you to check out Vision Transformers if you've been using CNN or any other kind of computer vision algorithm. Okay, so we've done this. We've looked at this. And now I want to turn your attention back to the presentation. Okay. And we're going to look at the conclusion. We have, I guess I kind of went a little bit fast on this one. I should have maybe gone a little slower. I realize I'm kind of a little bit early on this, but we'll look at the conclusion. So, what did we get out of this, right? We know that vision transformers are showing a strong performance in image classification, right? They're really doing a great job of choosing which images are which. We have an efficient handling of global context and spatial relationships. So we're able to actually get those. And does anybody remember how we got global context and spatial relationships through vision transformers? Something that's a little bit harder to do with some other computer vision architectures. No? Well, the way we did it was with a multi-head attention. And if we go back to this research paper, you can see that the multi-head attention is going to pay attention to each of these flattened patches and see how they relate to one another. Much like in a sentence, the transformer will look at how each word is relating to each other word. So it's really quite neat. All right, and then let's go back to here. We had that our atom optimizer is going to improve the training stability and the convergence speed. And then we had that the sparse categorical cross entropy is enhancing the computational efficiency because it's going to calculate that loss function that's really appropriate for what we need to do. And correct and incorrect predictions highlight the practical implications. So you could see over here, we were finding that even though the model does quite well, in some cases, unfortunately, there are some things you need to take into account, like shadows and contrasts, to really pick up on that flower. All right. So I'm actually gonna, before we go to Q&A, I want to actually try and run this thing because, and even if we can't get through the whole thing in an efficient amount of time, I want to just try a little bit because it would be kind of sad if we couldn't. So let's try TPU v2. Maybe we can get to TPU v2. What do you all think? Think it's possible? What if we even get just a CPU? You think it'll connect us to a CPU? That would be really nice. Wow, it is really not happy with me today. All right, so I guess we're going to try our backend with no accelerator. Oh, hey, look, it's attaching. Look at that. All right. So, I'm not sure what kind of processor we're running on right now, to be honest. Looks like we're on a TPU v2. Hopefully this is pretty good. Let's see. It takes a while to install these libraries a lot of the times. So unfortunately, the default Colab does not always come with these TensorFlow datasets and things like that, so you do need to install. Oh my. Oh yeah, we got to restart the session. Okay, so we've got that. That good. And let's keep going with our notebook. We did cell block 3 here, where we were loading in the data sets. Wow, this last one's taking a while to extract all of this. I mean, it's a lot of data, really. It's 600 megabytes, 660. It's a lot. Just wait here for a second while it extracts all of this. Could take a minute. Let's see how we're doing here. Looks like we finished that data set load. So we did the pre-processing, plotting the data. I think we're on to training now. So we got quite a bit of training to do. Fortunately, on these slower processors, it can take quite a bit of time. Hopefully, you were able to also get it going on yours. Why don't we just pause here? Maybe we could take a little break. We've been going already for over an hour on the stream. So why don't we take a break and we will let this model train. All right, folks. So I think we're probably not going to go through all 10, but we did go through one. So I just wanted to show you a little bit about that and how it can successfully train. Okay, well, why don't we go ahead and have our Q&A then? And does anybody have any questions about the Vision Transformer? I really hope you try to implement this in your next hack. The next time you're faced with a machine learning question. I promise if you use a better GPU, it's much faster. You saw my results earlier. We were getting done with the whole training protocol in just 5 minutes. And I think we've almost been waiting 5 minutes just for a single epoch to finish. It's like an order of magnitude difference between the TPU v2 and the T4 GPU. That's really cool to see how amazingly fast they have become. But yeah, any questions from the audience on that? All right. Well, I guess that will conclude it then for the for the workshop today. And I hope you all enjoyed and great work. If remember, don't forget to check in for this workshop. I'll actually post a link to that up on the screen. Let's see here. Get that going for you. Oops, just pasted the wrong thing in there. Here it is, the check-in link. And another thing I will post is a link to the slides. If you are interested at all in checking on those, you're more than welcome to. Okay, we have a question about transformer encoders. And I have a little bit of information on transformer encoders in the slides. So if you go to this second section here, you can see that the self-attention mechanism, we talked a little bit about the self-attention mechanism, but the transformer encoder is really, it's sort of like, how are things related to one another, right? How are we connecting each of these together? The feed forward layer is another portion that we didn't really talk about as much. And the encoded patch embeddings is you're basically attaching the position of the patch to that patch's information that's allowed to be used for training. So it's really super similar to how a regular transformer works. You can just think of the transformer encoder as relating the different patches to each other. Okay, both gathering, extracting the information from each patch, and then also relating it to every other patch. Okay, so I highly recommend to check that out. Any other questions on this? Maybe I'll post the. I think of course I have to get rid of these insert outline here, but I'm going to put on the introduction page. I'm going to put the link to the Colab notebook so that you also are not going to lose that. Because I know how things can just kind of get lost sometimes. VIT paper. I'll put the VIT paper too. Somebody did ask for the VIT paper. Amazing that this was published back in 2021. Seems like a long time ago in machine learning world. But there they are if you wanted to take a look just on this second slide here. All right, G Gross V said, mine ran. That's awesome. I'm so glad. You probably got access to a T4, didn't you? And Vita says, thank you. So yeah, thank you, everybody. I'm sorry again. This is the first time running the Vision Transformers workshop. So sometimes on the first run, I can never know exactly how long things are going to take. So, next time we run it, maybe I'll add some more to it, and we can actually get a little bit more into the weeds of it. Even maybe explore some other transformers, fine tuning, how the patch size influences things. But for this one, we'll have to leave it there. But yeah, great having you all along. All right. Take care, everybody.